Imagine a star, not our friendly life-giving sun but a celestial monster of scale. Artist's rendition of UY Scuti glowing deep red. Imagine placing it at the center of our solar system, its surface stretching past Jupiter's orbit. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, all of it becomes part of the star itself. This isn't science fiction. This isn't a lab thought experiment. This cosmic leviathan is real. It has a name, UY Scuti, a bright red hypergiant, a rare, spectacular class of star. It sits about 9,500 light-years away in the constellation Scutum. From Earth it looks like a faint speck, but that dot hides a secret. It strains our models of stellar physics. How can something so massive hold together? What forces forged such a titan? Its existence sends ripples through our understanding of stellar evolution. So let's begin our journey. Peel back the layers of this cosmic onion. Travel across space and time to understand this star and its phenomena. We'll explore the very nature of size, the bizarre worlds that might orbit such giants, the violent finales that await them. UY Scuti's story is more than a big star, it's a gateway to the profound, the mysterious, the truly mind-bending. Are you ready? Let's go. Let's try to wrap our minds around the sheer size of UY Scuti. It's a task that bends the imagination to its breaking point. We often use our own sun as a yardstick for the cosmos. It's a respectable star. You could fit about 1.3 million Earths inside the sun. That's a big number. But when you compare our sun to UY Scuti, our star becomes an insignificant grain of sand next to a colossal beach ball. UY Scuti has a radius estimated to be around 1,700 times that of our sun. Its volume is staggering. You could fit nearly 5 billion suns inside of it. Yes, 5 billion. Let that number sink in. Consider the speed of light. Light is the fastest thing in the universe, traveling at 186,282 miles per second. Light from our sun takes about 8 minutes and 20 seconds to reach Earth. Now imagine light trying to go around UY Scuti's circumference. It wouldn't take minutes, it would take hours. A commercial airplane at cruising speed would take over 1,000 years to fly around its equator. Our human concepts of distance and travel become utterly meaningless. This object operates on a scale we weren't meant to intuitively grasp. A bloated, dying king, magnificent in its final sprawling glory, reminding us size and mass are not always the same. The universe isn't just a collection of stars and planets scattered randomly through space. It's a dynamic, interconnected cosmic web, a grand tapestry woven from gravity and time. Massive stars like UY Scuti don't exist in isolation. They are part of a colossal, invisible dance with other cosmic entities. These stars are often found in bustling stellar associations or open clusters, gravitationally bound families of stars that were all born from the same giant molecular cloud. They move together through the galaxy, their combined gravity influencing their surroundings, stirring up gas and dust, and potentially triggering new waves of star formation in their wake. These giants also interact with some of the strangest and most enigmatic structures in the universe, cosmic voids. These are the vast empty spaces between the filaments of the cosmic web, regions of space with a much lower density of galaxies, stars and matter. A star on the edge of a void experiences a peculiar gravitational environment. And then there are the ghosts. When a massive star finally dies, it doesn't just disappear, it leaves behind a spectacular remnant, a ghost of its former self. Imagine a black hole, the ghost of a long-dead giant star, where even the largest stars are just dancers in a grand cosmic choreography. The universe of giant stars is not just about the stars themselves but also about the bizarre and extreme worlds that might exist nearby. While a planet orbiting close to a hypergiant like UY Scuti would be vaporized, what about planets in more stable, distant orbits? Consider the hypothetical diamond planet, 55 Cancri E, a real exoplanet, a super-Earth orbiting a star in Cancer. Based on its density and stellar composition, some scientists think it could be carbon-rich. A surface of graphite, a thick interior layer of pure diamond. Imagine standing there. A nearby sun dominates the sky. The ground, shimmering crystalline carbon. Planets orbiting pulsars. A pulsar, a rapidly spinning neutron star. The super-dense remnant of a supernova. A cosmic lighthouse, sweeping radiation beams. The last place you'd expect planets, yet we found them. The first exoplanets, Poltergeist Phobator orbiting PSR B1257+12, hot Jupiters, water worlds, rogue planets. Each discovery is a puzzle piece, showing world-building recipes far more varied than our solar system. So, how do we know any of this? How do we measure a star that is 9,500 light-years away? We can't just send a probe with a tape measure. The answer lies in a clever field of cosmic forensics, using light itself as our primary tool. One of the most fundamental methods is parallax. Imagine holding your finger out in front of your face. Close one eye, now close the other. Your finger appears to shift against the background. We do the same with stars. Observe a star from one point in Earth's orbit. Then again, 6 months later from the opposite side. The slight apparent shift against distant background stars lets us calculate distance with trigonometry. Once we know distance, we can get true brightness, luminosity, measure apparent brightness from Earth, how much light reaches us. Apply the inverse square law, light falls off with the square of distance, so we calculate source brightness. Uy-Scuti's luminosity is over 340,000 times the sun's. That staggering output marks it as a hypergiant. Spectroscopy splits starlight into a spectrum. The dark absorption lines reveal chemical elements and temperature. Astronomers use interferometers. They combine light from many widely spaced telescopes. The VLT interferometer in Chile directly measured Uy-Scuti's angular diameter. With angular size and parallax distance, astronomers calculate its physical radius. We are spies in the dark, using photons as informants. Every star from the smallest brown dwarf to the most colossal hypergiant begins its life in the same place, a stellar nursery. These are not quiet, peaceful places. They are vast, cold, dark clouds of molecular gas and dust churning with unseen turbulence. These clouds, sometimes spanning hundreds of light years, are the hidden wombs of the galaxy. Deep within their opaque shrouds, gravity begins its patient work. It pulls denser clumps of gas together, causing them to collapse under their own weight. As these clumps, known as protostars, contract, they begin to heat up, their cores growing hotter and denser over millions of years. The birth of a truly massive star like Uy-Scuti requires a particularly dramatic start. It needs to be born in the heart of a massive, dense core within the molecular cloud, a region with an enormous reservoir of material to feed upon. As the protostar grows, its gravity becomes immense, pulling in gas and dust at a furious rate. This process is a chaotic battle. For a massive star to form, the inward pull of gravity must overwhelm this outward radiation pressure. It's a violent, messy birth, shrouded in cosmic dust. For a hypergiant star like Uy-Scuti, life is fast and furious, and its death is one of the most spectacular events in the universe. But the final explosion is preceded by a long, dramatic, and unstable death rattle. As the star exhausts the hydrogen fuel in its core, it begins to fuse heavier elements, helium into carbon-carbon, into neon heavier and heavier up to iron. Each new stage of fusion provides less energy and lasts for a shorter time. The final stage, silicon burning to create iron, might last for only a single day. Iron is the end of the line. Fusing iron doesn't release energy, it consumes it. This is the star's point of no return. Once an iron core builds up, the star's fate is sealed within seconds. With no more energy pushing outward, gravity wins catastrophically. The iron core, roughly the size of the Earth but with the mass of more than one sun, collapses under its own weight. It shrinks from thousands of miles across to just a dozen miles in less than a second. The outer layers are left in freefall, plummeting inward at a quarter of the speed of light. This is the silent, terrifying moment before the universe-shattering bang. This shockwave is the supernova. It rips the star apart, releasing more energy in seconds than our sun will in 10 billion years. For all that we have discovered, the universe remains a place of profound mystery. The existence of stars like Uy-Scuti pushes our models to their limits. It also points toward even deeper questions we are only beginning to ask. What is the absolute maximum size a star can attain? Is there a physical limit? A cloud of gas too large to coalesce into a stable star? Or does it collapse directly into a massive black hole? We know that everything we can see makes up only about 5% of the cosmos, 5% ordinary matter, 27% dark matter, 68% dark energy. These are not small gaps, they are colossal voids. We are like explorers who have mapped a tiny island and just realized it's part of a vast, unseen continent. Even things we think we understand, like black holes, still hold secrets. Stephen Hawking proposed black holes slowly evaporate by emitting Hawking radiation. This idea links gravity, quantum mechanics, and thermodynamics, but it leads to a paradox. What happens to information that falls in? Does it vanish forever, violating quantum laws? Or is it somehow preserved? The black hole information paradox is a battleground for theorists. Its resolution could lead to a unified theory of everything. We have journeyed from the mind-boggling scale of a hypergiant star to the theoretical worlds of diamond planets and the silent death of failed supernovae. We've seen that the universe is not a static, predictable machine but a living, breathing, evolving entity. The story of UI Scuti is not just about one star, it is a portal, an invitation to contemplate our place in this vast, magnificent cosmos. It's a reminder that the world we see is one tiny, precious corner of a grander reality. The universe is the ultimate laboratory, its experiments play out on scales of space and time we can barely comprehend. This journey of discovery never ends. The next time you look up at the night sky, don't just see a random scattering of lights. See a universe full of unanswered questions and untold stories. So I ask you, what fascinates you the most? If you enjoyed this cosmic journey, subscribe for more explorations into the universe. Like this essay, share it with a friend, leave a comment below, tell us what cosmic mystery ignites your imagination. Let's explore it together.